So I guess it's time to start. Thank you very much for coming, and we are very happy to start our meetings in Quantum Club, and it's the first meeting of this club, and me, Alexandra, Elliot, and Stefano, we just organized it here in University of Geneva, and the main idea of this club is to cover the very broad range of quantum areas and to give you an intuition of how things work, which ideas are created, and which methods are used in each of this area, and to make it in a very understandable way. And also we are going to have two more projects. One of them is very popular lectures for the people without technical background, and if you know anyone who is interested in them, please give them links of our social media. And the second project, which is not about this lecture, it's going to be a series of workshops for advanced PhD postdoc students, where we are going to share our ideas, our problems, and we'll try to solve them, but it will follow. And today we are going to have the first talk given by Professor Wolfgang Tittel, and Wolfgang did his PhD here in Geneva University as well, later worked in Canada, and now he's a professor here and in Constructor University. And the main focus on his work is about communication on the long distances, and today the talk will be about quantum networks and quantum memories there. But before that, I will give a very brief warm-up talk, which is quite popular, I would say, and describe such phenomena as entanglement and quantum teleportation, which are quite well-known ideas in quantum mechanics. And I will start with the very basics. So we can talk about information, and if we're talking about classical information, we can usually appear the following terms. So we have bit, so it can be 0 or 1, and as far as we have only two states, we can describe them like these two vectors. So nothing complicated, and we can have conjugated vector, and this notation, just notations which we usually use in quantum mechanics, and they called bracket notation because we can have bra and ket vectors. So that's very simple, and that's if we're talking about classical computers, and in classical computers we can have bit, so we can have current or have not the current. But if we're talking about quantum mechanics, we can have a high dimensional space of our states, and we can have any possible superposition of these two states. So we can have any state which can be written in this form with the norm that A and B coefficients satisfy this condition. So actually, we can describe this state as the state on this sphere, and this sphere called the Bloch sphere. So for example, we can have state which is called plus, and actually it's a superposition of 0 and 1, and here we have similar coefficients for 0 and 1. And it means that, for example, if we have our state in plus state, our system in the plus state, and we can measure it with the measurement device, which can have, which set in the basis 0 or 1, that with 1/2 probability we are going to have 0 state, and with 1/2 probability we are going to have 1 state. And the same with -1 state. So here we have just two different bases, one of them explained in terms plus and minus, and another one 0 and 1. And another important property of quantum mechanics, then after the projective measurements which we done on our system goes to one of the state it was measured. For example, initially we had state in our plus, and after the measurement we measured that the state was in 0 state. It maintained in 0 state after the measurement. And now we introduce the superposition. But actually, that's not a property which made our system quantum. For example, in classical system, which we can also have the similar system. For example, we have this pendulum, and we know that the motion of this pendulum we can describe as motion of two separated modes, shown like this. So it's studied on the very first course of classical mechanics, and superposition is something very common. So we can have this property in waves when we consider light or acoustic waves. So it's the same here. But what can we do in quantum mechanics, and what is really special there is an entanglement. And actually here we can consider two systems. And here the first number here is for the first particle or for the first system. And the second number, like 1, 0 here, it's for the second considered system. And if you're talking about it, that we can say that if we have first system in state 0, then the second one is for sure in this state 1, and vice versa. If we know for sure that the first system in the state 1, then the second one in state 0. To make it more intuitive maybe, here is analogy, not complete, and I'll a bit explain why it is not complete a bit later, but we can have Alice, and Alice have a magic bottle with a liquid, and the bottle can do whatever Alice wants. And Alice can have only 2 wishes. For example, she wants to become smaller or bigger. And there is a box, and inside this box, the second bottle with the same magic liquid. So both of them, they have property that they can make Alice smaller or bigger, but at the same time, they're entangled. And what does it mean? That, for example, if Alice decides that she wants to become smaller and drink from this bottle, then immediately the liquid in this bottle became the liquid which can make Alice bigger, and vice versa. So, for example, if Alice drinks the lilliput liquid from this bottle immediately have the giant liquid, and here if it has a giant liquid and Alice realized that she wants to become bigger, and here we have the lilliput one. And actually, after Alice made her decision, she knows for sure that inside the box there is the opposite liquid. And it can happen even if this box is on the moon. So it doesn't depend on the distance between them. We know for sure the state of another system immediately making the measurement on this state. And again, here we use the property that after the measurement, our system collapses to one of these states. So if we measure this state and we obtain 0 for one system, then the total system is in this state. But another interesting property of entanglement in quantum mechanics is that we can write this superposition not only in these bases, but in any other basis, and the correlation between these 2 systems remains. So here we can consider that here it's minus, so it's different phase, but still in any basis we choose, we will have this correlation. And talking about entanglement, there are 4 very important states for quantum mechanics. They're called maximal entangled states because here we can obtain maximally possible correlations, quantum correlations between 2 systems, and they're called maximal entangled state. And in the space of 2 systems, they form the basis. So in the space of 2 systems, we need 4 states for the basis, and these bases from this maximal entangled state called Bell basis. And knowing about Bell basis, we can go to the quantum teleportation. But it's important to understand that we will not talk about transfer of the matter, and we will not talk about cloning the system. So what we are going to do, we want to clone unknown quantum state, because there is no going theorems in quantum mechanics, and they forbid these actions. But what we are going to do, we're going to transfer the unknown quantum state from one system to another. And this is called teleportation. So, for this protocol, so to realize quantum teleportation, we need 2 actors, and one of them we will call Aphrodite, and another one Bacchus. And in this system, we assume that Aphrodite has a qubit, and here I use the superconducting qubit as an image, and this qubit is an unknown state, so Aphrodite doesn't know about the state of this system. And Bacchus has his qubit, and he wants to have exactly this state on his qubit and measure it. The state is unknown. And to perform this protocol, we need the second qubit on Aphrodite's side, and now we want to make these qubits entangled. So we create the very well-known state here, which is one of the Bell state, and we make this qubit in a connection. And later, we can write the state of the whole system in the following way. So again, on Aphrodite's side, we have qubit 1, and for qubit 1, we have the first number here. For the qubit 2, which is entangled with the Bacchus qubit, we have second number in each of this part of the superposition, and Bacchus qubit has number 3. And again, here's the third qubit. But now we can see that on Aphrodite's side, we have these combinations of qubit states, and now we can recombine this into the Bell base. And if we want to do this, we are going to have the following long state. But to make it simpler, for Aphrodite we have 4 options, and each of these options corresponds to a certain Bell state from the Bell basis, and for each of these Aphrodite Bell state, we have a certain state for Bacchus. And now Aphrodite can perform the measurements in the Bell state and realize which state she has. And for example, Aphrodite performed her measurements and she got 5+ state. Now she can call Bob and say that she obtained this state. Knowing this information, Bob realized that now he has this state. But it's not exactly the state he wanted. So originally the unknown state was in this form. And now Bacchus knows that to put this state into this form, he needs to perform this action. And Bacchus can manipulate his qubits. And for each of these combinations, Bacchus knows exactly what should he do with his qubit to obtain the initial state which was on the Aphrodite side. So what we need to know the state of Aphrodite, and knowing this information, Bacchus can perform some operation on his qubit and got the state he wanted. This is a protocol called quantum teleportation, and here we assume that actually we can manipulate our qubits, and we have qubits. But now we can talk about the systems which we can use for the qubits, and there are very different ways to realize them. And we can use photons, for example, which is quite popular here in Geneva, I guess. We can use Rydberg atoms placed in the cavity. We can use quantum dots. We can use diamonds with NV centers, so where actually the atom replaced by nitrogen and the vacant place. We can use it also in particle physics, which is not very popular, but it's still possible to use particles as a qubits, and actually flying qubits, which makes photon not the only flying qubits. And also we have superconducting qubits and trapped ions. And about these two systems, we're going to have the talk in 2 weeks, so you're very welcome. We are going to have discussion and comparison of these two systems, and later we'll cover other systems as well. But now let's go back to the teleportation and see how it can be realized with photons. So again, we have Aphrodite and Bacchus. And let's say that we have a source which produces entangled photons in between them. And actually it can send these photons one to Aphrodite and one to Bacchus. And another photon from another source can come to Aphrodite, and we have the same system. So here we have an unknown state we want to teleport, and here we have entangled state. It can be any entangled state. But later, Aphrodite performed the measurements in the Bell basis, and it takes time. So if we assume that here we have more or less the same distance, then while Aphrodite performed the measurements in her basis, the photon which came to Bacchus is already very far away, and Bacchus cannot measure it. So the way to solve it is actually to send the photon at the same time with the photon which go into Aphrodite. Later, store them somewhere in the memory, and this device called quantum memory, and later send to Bacchus. So these devices, they can be realized in very different ways, and the very easy way is just to have the optical fiber, the photon propagates much longer on the Bacchus side. But also there are many more possibilities, and one of them is the rare earth crystals, which Wolfgang is going to talk today about. And on here I conclude my talk. And thank you very much. If you have any questions, we can discuss it later. And we are going to have apéro, not here, but in the nearest building in the dacha after the talk. And we can discuss all the questions you have. Thank you very much.
Thank you, Anne. That was a fantastic warm-up talk. All right. Well, thanks a lot for this very nice invitation to come here to talk in front of you. In particular, I realize it's the first time we have this quantum club, and I feel a little bit under pressure right now, but I hope I will do as well as Anne just did. Maybe let me just start with a question to you. If you think back the last 50 years, I do realize most of you are not at that level yet, but what do you think, which technological development over the past 50 years has had the biggest impact on our lifestyle?
Transistor.
Close.
Semiconductors.
Close. I will say close anyway, because I just want to be nice. Look at the slide. There is something there.
Internet.
The internet. Yeah, so I think the internet really has terribly, nicely, whatever you want, really affected our lifestyle. And right now there is not a single day anymore where we don't send emails, where we don't look up information online, where we don't post information online, where we don't fill out online forms. Yeah, and well, this was all enabled by the possibility of encoding information in bits. And surprisingly, it turns out that as you change the carrier of your information from a bit to a quantum bit, and we have just heard how that works, in practice at least, so we talk about superpositions of zeros and ones and entanglement between zeros and ones. But as you do that, it turns out that you can discover completely or fundamentally more powerful functionalities. Like the possibility of having Alice and Bob, or Aphrodite and Bakshas, who can distribute a secret key, a key that they can use later on for encryption purposes. And once it's distributed, they can figure out if anybody listened to that distribution, in which case they wouldn't use that key, or vice versa. If they see that nobody listened to this distribution, then they are sure that they have a private key and that they can use that for encryption purposes. Yeah, this is something you cannot do with normal encoding, with classical encoding, but if you use quantum encoding, it turns out you can do this. Yeah, you can also think about computation, or rather network computation, since we talk about the quantum internet. You can think about network quantum computers. You can think about what we call blind quantum computer, where there may be a powerful quantum computer in some other country, or maybe in my own country, but not where I'm working. It turns out I can encode a computational task into quantum bits, send this task in a quantum encrypted manner to the computer. The computer calculates on encrypted quantum data, sends the reply, the response, the result of the calculation back to me, still encrypted, and only I can decrypt it, only I can learn what I asked the computer to calculate, because only I know how the original question was encoded. We refer to that as blind quantum computing. And again, it's a primitive that quantum mechanics promises or says we can do it in a provable, secure manner, while classical encryption like that is not sufficiently secure. You can also think about distributed quantum sensing. You can think about having two optical telescopes that gather light from distant stars. And now it turns out if you bring this very weak signals that the telescopes gather together, and you make a joint measurement there, and suddenly the resolution of your telescopic system corresponds to the distance between these two telescopic systems, and not anymore to the radius or diameter of each individual telescopic system, as it would be if you use standard means. Yeah. This has been done with radio waves. You may have heard about the square kilometer array. There's one in Australia and I think one in South Africa. That's done with radio frequencies. With optical frequencies, it's a bit more difficult because you really have to bring very weak signals together without losing them. And it turns out that there are proposals how we can use quantum communication in order to improve that task. Yeah, so yeah, all this may become possible with the quantum internet. And now normally, as you discover new functionalities, well, you also have to work on new materials, on new protocols. There's a lot of things that you have to develop. But sometimes you're lucky. Yeah, and sometimes it turns out that you can base what you would like to do on materials whose properties are already quite well known. Yeah, and this is something I want to tell you today, which is how you can use rare earth iron doped crystals, which are heavily used in solid state lasers. So these are things that you can buy commercially since many, many years. Yeah, if you think about the green laser pointer, the more modern version of this one here, this often starts with a rare earth iron doped laser, which is the frequency, whose light is frequency doubled to give you the green light that this thing cannot create. Yeah, but then it's also used in material processing and ophthalmology and so on. So a lot of uses for rare earth iron doped lasers. And here we also like to use rare earth iron doped crystals, however, under modified operating conditions. For instance, we will operate them at very low temperatures, of around 2 Kelvin or so. And often, in order to increase the coupling to light, we have to embed these rare earth iron doped crystals into cavities. And we'll tell you a little bit what we are doing and what we would like to achieve and how we are there right now. Yeah, but maybe before, let me tell you something about how I think about this quantum internet. Yeah, so this is a very unrealistic but quite nice picture, how it will hopefully look like one day. In the way I picture a fully quantum-enabled internet, one that allows us to do all these tasks that I just fleshed out, is that while we have nodes of the internet in which we have, well, it's called quantum bits that are stationary. A superconducting qubit, an atom, an ion, something that doesn't move. into which we can encode quantum information, meaning whose states we can prepare in arbitrary superposition states. Yeah. We want more than one, we want neighboring ones so that we can couple them together and we can think about quantum information processing or quantum computing. Yeah. So I would like to have these type of things in these nodes. I would also like to be able to connect these different nodes, and that can only happen through the exchange of photons, because a photon is the only particle that we can send over long distance without it being absorbed, without that it changes its state in an unpredictable manner by interacting with the air or whatever is around. So we need also to have emitters in those nodes that allow us to send photons across the node, or maybe create even entangled photons, and we have just heard about quantum teleportation where entanglement plays a huge role. Yeah, so I would also like to have these type of things listed here. And then it turns out if the distance over which I would like to send these photons, or maybe better, the distance across which I would like to establish entanglement is too large, or better, the loss between, let's say, this node here and this node here is too large to send the photon directly, but then I have to use something that we refer to as a quantum repeater. Yeah, and you know about repeaters in classical optics, I think. These are just amplifiers for light. If I send a pulse of light, and that is what is being used in today's internet over optical fibers, the intensity of the pulse of light decreases exponentially as the pulse travels down the fiber. And at some point, you need an amplifier that boosts it up to its original level, and that decays again, and you boost it up, and it decays again. So we need something similar for photons and for quantum states. Only the normal way of amplifying light doesn't work in our case, because this would correspond to cloning of a quantum state. And as we just heard, this is something that quantum mechanics, or the linearity of quantum mechanics, does not allow us to do. So we need to do something different. And this something different, well, it does require so-called quantum memories for light. It's a bit like your hard disk that you can use in order to store an email, a photon in this case, until another email arrives that tells you what you have to do with the first photon. And for this, you have to keep the photon on hold, but the photon travels with the speed of light, which can be nice, but for this task, it's not. Yeah. So the elements that I'm talking about for these quantum internet, but we also require these quantum memories for light. Yeah, so you see there are different elements that require atoms, stationary materials, and interactions with photons. We call these often quantum interfaces. You also need detectors for photons and so on. This is technology that's already very well developed. I will not talk about that. So we'll focus here on quantum interfaces between light and matter for the applications that I have told you before. Yeah. And now what we would like to have, of course, is not one particular material that allows us to create quantum computing nodes. And maybe they operate at 30 millikelvin temperature and at very small magnetic fields and this and that and those. And then we also need sources of entangled photons that have to work at 100 Celsius. And so you see, you easily come to lots of technology that is not compatible. What we are set out to look at, to research, is there a possibility to find a single material candidate that can be used for these three different applications or these three different elements of a quantum network that I've just fleshed out? Quantum computing, sources, and these memories for quantum repeaters. Yeah. And in addition, we would love to have something that we can integrate on chip in order to create, at some point, technology that can be mass-produced, that is small, and that can really be used. Yeah, so let us see a little bit how we're doing there. And more precisely, what I would like to cover today is to tell you something about rare earth ion doped crystals. Because for me, this is this type of material platform, and in my opinion, the only one that allows us to do all this on the same platform. I will tell you about how we can create single photons based on individual rare earth ions that are coupled to a nanophotonic cavity. And what you see here is a picture of such nanophotonic cavities. Well, what you see here is some kind of vertical stripes with holes inside, quite small. You see the scale bar here. I'll tell you a little bit more why that is actually cavity and what that has to do with the emission of single photons from single rare earth ions. So I will tell you more about how we can actually create quantum memory for light, in which case we don't use a single rare earth ion, but a large ensemble of rare earth ions, maybe 10 to the 20 or so. And here you see a crystal with a standard waveguide inside here that is doped with thulium ions and that we have used, for instance, to store members of entangled pairs of photons. Yeah? And then I will conclude my talk. So I have a lot of things that I can tell you, and probably much more than I've prepared here. If you have questions, just ask. I'm fine to start just a discussion. If there are things that I won't cover today, I don't care. The only thing that I would like that you get out of this and say, oh, this is cool, this is great, I've learned something. Yeah? And if you want more, I'll just send me an email and I'll make sure that you get proper replies. All right, rare earth ion doped crystals. Well, remember the periodic table? Anybody? Good, nobody. No. Okay, the rare earth ions is a series of elements from lanthanum here to lutetium. Yeah, well, these are, more precisely speaking, the lanthanides. The rare earth ions also include yttrium and scandium. So we're talking about those, but in my field we refer to those as the rare earth ions. Now, what is so special about those? If you remember how to go through the periodic table, starting with hydrogen to helium and so on, but every time you change the element, you add an electron, a proton and maybe a neutron. And these electrons, they form orbitals. Orbitals form shells, and when the shell is full, you move to the next shell. That's kind of the standard procedure. Yeah, but there are exceptions to this rule. Sometimes the next shell is being started before the shell before is fully filled. Yeah, and that happens, for instance, when you fill up the shell number 4. Before this is filled, before you start filling up the so-called 4f orbitals, but electrons start actually populating the shell number 5 and even start populating the shell number 6. Yeah, and this is when you come to the rare earth ions, when you're here, this is when suddenly electrons go back into shell that is closer to the nucleus and populate the 4f shell, or the shell number 5 and shell number 6 are already populated. Yeah, so the shell number 4 is not full, which means it's possible for electrons to take on different positions within the 4f shell. And these are so-called 4f transitions, and these are these transitions that are extremely interesting and have properties that I will tell you a little bit about on the next slide. Yeah. Now, these transitions are heavily used in classical and now also in quantum technology. What I show you here is a so-called decay diagram, where a lot of different rare earth ions have been tabulated here. And what you see here are the different transitions, the different energy levels that are allowed or that exist in these rare earth ions. And then I've shown in red transitions that are being exploited for solid-state lasers. For instance, you see the 1064 nanometer laser, which is, if you double it, gives you the green light in the laser pointer. You see the 1550 nanometer transition that is used in erbium doped fibers for fiber amplifiers. And you see some other transitions that you may not know about. Yeah? Just saying, okay, there's a lot of commercial interest in this type of crystals because of lasers. In green, I've indicated transitions that are currently being researched for quantum technology, both for quantum memories as well as for single photon emitters. You see, for instance, here a transition at 600 nanometers in praseodymium. Several transitions, and the ones that we have focused on so far is this transition in erbium at 1532 nanometers and a transition in thulium at 795 nanometers. Yeah, you see just two examples. What you have here is a thulium doped crystal. This part here, that includes the waveguide, an area that is doped with a different material, which raises a little bit the refractive index. And then if you inject light into this waveguide, well, it will stay within that waveguide. And you see that actually it's glowing under illumination with red laser light. So you see where the light is propagating. Yeah, we've done a similar experiment, in this case with an erbium doped optical fiber. Well, you see a fiber coming in here, maybe one coming out here. The fiber is wrapped around a copper coil, and in both cases we have to apply a magnetic field in order to improve the properties of these rare earth ions to make them suitable for quantum memory. All right, so what is so particular about rare earth ions? So the first thing is these 4F transitions are often in the visible and in the near infrared. And these are the transitions, these are the wavelengths that we're interested in for communication purposes, in particular over optical fibers. Yeah, so this is good for quantum communication. Then if you look at a large ensemble of rare earth ions, you see that each ion has a slightly shifted resonance frequency. And you can think of this a little bit like the Doppler shift. Yeah, if you have an atomic gas at room temperature, you have atoms that move towards you, whose resonance frequency is shifted towards the blue. You have atoms that move away from you, whose resonance frequency is shifted a little bit more towards the right. So if you look at everything together, you see that the resonance line, the absorption line, can be very broad. Your atomic gas absorbs a very broad frequency range, but it may well be that if you were to address an individual atom, the resonance is very, very narrow. And you get the same thing for rare earth ions, only in this case it's not movement. These ions are inside the crystal, they don't move anymore. But in this case, this is due to lattice defects, strain, different types of charge compensation, so imperfections of the crystal, which you find for every crystal. Yeah? So you also have this inhomogeneous broadening. That's actually quite a nice thing, because the larger it is, the larger in frequency space is the light that you can absorb. Or if you think of Fourier transform, the shorter a photon can be that you can absorb, and the shorter a photon, the more you can pack within a second, so you can increase the rate of communication. So having a large absorption profile is actually something that we absolutely would like to have. Yeah. Now another thing is, if you excite your rare earth ions, let's say from the ground state level here to an excited level, well, the lifetime up here is extremely long. It is often milliseconds, 10 milliseconds, sometimes even tens of milliseconds, which is huge. Yeah. Now, this is a little bit problematic at first glance. Because if you think, well, I would like to create a single photon source. The best single photon source is a single atom, ion, rare earth ion, except for you don't want these long lifetimes. Because what you would do is have the ion, the atom in the ground state, send a pulse of light to excite it to the excited state, and then if it's only a single atom, a single emitter, at some point you get a single photon out. But now, if the lifetime in the excited state is 10 milliseconds, this will happen on average only 100 times per second, and this photon will be emitted in any direction, so the probability that you can actually use it in your optical fiber network is basically zero. It is very, very difficult to observe single photons from individual rare earth ions. So this sounds at the first glance as a bad property, but we'll come back to that. You can actually turn it around and make it a good one. And the first thing that is good about it is that if you cool these ions down to very low temperatures, let's say Kelvin or so, then the homogeneous line width, so the resonance width of a single ion, becomes extremely narrow, or the coherence time, which is the inverse of that, becomes very, very large. Now you have to know that the upper limit of this coherence time that you would like to be large is 2 times the lifetime of the ion in the excited state. So if you want long coherence, which is related to how long you can store information in rare earth ions, but you want this long excited state lifetime. So here's actually a good property. It's at the heart, it's at the origin of these very long coherence times, where milliseconds have been measured before. So this is good for quantum memory. Another thing, well, if you apply magnetic field, different states, here they often split into nuclear Zeeman levels, for instance. Yeah, and the coherence time between these levels here, well, I think the longest coherence time that has been measured was a couple of hours, which is really huge. And that is great if you think about encoding a quantum bit in superpositions of these two states. It is also great if you think about creating a quantum memory approach which stores quantum information from a photon in superpositions of these two states, where you can also achieve very, very long storage times. Yeah, so that's also a great property. And the last one is that depending on the host in which you embed your rare earth ion, it turns out that if you excite one ion, the electric field around it does change. Now, if there's another one very close by, it will see the changed electric field. You may have heard something about the Stark shift. This leads then to the fact that the level structure changes a little bit. Levels shift. Yeah? And that in turn allows you to make a transition or a transformation of the second ion based on the state of the first one. If it's excited, you may be able to make a transformation of the second one. If it's not excited, nothing would happen. Yeah? And then you get into this realm of controlled quantum operations. You go into the realm of quantum computing. Yeah, and I won't talk much about this, or not at all. If you have questions, I can tell you more about this later. Yeah? So in short, this is really promising for the different elements that I've talked about. This is promising for quantum computing. This is not yet promising for single photon sources, and I will tell you how you can turn it around. But this is very promising for quantum memory for light. So I already checked 2 of the 3 applications that I'm interested in. So this is the bad one, as I said, for a single photon source. You would excite the ion from the ground state to the excited state, and then just wait until the photon comes out, in our case, for a very long time. But there's a trick that you can run. What you can do is you put your single ion, here's again the cartoon, into an optical cavity, an optical resonator, so here you see two different mirrors. Yeah. And now, when you want to describe what is happening with the ion, well, several things can happen after you excite the ion. Number one, it can just spontaneously decay under the emission of a photon from the excited state to the ground state. And that happens at the decay rate gamma. The other thing that can happen is that the ion exchanges energy with the electromagnetic field inside that cavity. And that happens with rate g. Yeah. Now, what you would like to have is that this rate g of the exchange of energy is much larger than the spontaneous decay rate, such that as soon as you excite the ion, well, the energy is transferred to the electromagnetic field. So you don't have to wait for the ion to decay naturally because you have forced it to lose its energy already. It's right now in that cavity. But now you have to watch out. You don't want the coupling to be so strong that the energy goes back to the ion and back to the field and just oscillates between the two. That's what we call the strong coupling regime. You would like that the decay rate through these mirrors that are not perfect is larger than the coupling rate here, such that as soon as the energy is, in terms of the photon in this cavity here, well, the photon will leak out in the direction, in the mode determined by the shape of the cavity mirrors. And now suddenly you have a single ion that emits photons at a high rate, because of G, into the direction that you're interested in. So this is called the Purcell effect. And if you look at that in more detail, you find there is an enhancement of the spontaneous emission rate from gamma naught, this gamma here, it's just the gamma should be gamma naught, to gamma prime, which is given mostly by the quality factor of your cavity. That tells you something about how long can you store energy inside of your cavity, or you can also think of it like the resonance width, the width of a resonance in that cavity. And you have to divide it by the mode volume, which tells you something about how confined is the light, the electromagnetic field inside this cavity. This is more precise here, so you see it's basically the integral of the intensity as a function of the position times the dielectric constant here, with some normalization factor. Yeah, so if you look at that, you also see, well, this volume here, this mode volume, is measured in terms of the wavelength to the power of 3. And since the wavelength of light is so small, you have to find a way to make cavities with extremely small mode volume. So just taking two bathroom mirrors and putting them close to another would not do the trick. Yeah, you need something a little bit better. So I think a very important step towards this a little bit better was done or shown in 2009. Had nothing to do with Purcell enhancement or Purcell effect, but in terms had something a lot to do with creating really good cavities for these type of things. This was done in the group of Marco Loncha in Harvard, and what he did is he created a so-called nano-beam, a very thin wire of silicon that was suspended. I'll tell you later on how you can actually do that. Yeah, and in this wire, through which light could propagate, he made small holes at periodic distances. Now, if these distances were really periodic, we would call that a so-called Bragg mirror, or photonic bandgap material. It turns out that if you set light in, well, the reflections at all these different holes here, or these areas with different refractive index, would lead to the fact that light will not propagate inside this device, but would all be reflected. Now, if you look carefully at the center here, the holes have changed a little bit. If you zoom in, you may see that the holes here are a little bit smaller than outside. And in the extreme, you can even say, okay, let's remove these holes here. It's not perfect, but you could do this. So you can think of this like, okay, there is a mirror here, and there is a mirror here, and suddenly we have this resonator with two different mirrors. And if you analyze the properties here, you find that these numbers won't tell you anything. You find that the quality factor Q is actually very high, and the mode volume is actually very, very small. Yeah, so it's these type of cavities that promise, in principle, strong Purcell enhancement, the possibility to see single ions from single rare earth, single photons from single rare earth ions. Now, this was done for the first time back in 2018. two groups in the US demonstrated indeed the observation of single photons from individual rare earth ions. And there were two approaches. One from André Ferrand's group at Caltech, where he did something, he built something that he refers to as the inverted Toblerone structure. You're all Swiss, you all like chocolate, so I think you can recognize the triangle just upside down. Yeah. So he used a rare earth ion doped crystal and then used what is called a focused ion beam. Ions that are focused on the substrate and they remove some of the material in a very precise manner. And then you can create these trenches and you can also create these triangles. And then what you have here is a waveguide with a repetitive arrangement of material and no material, like holes and no holes. And you can show that, or he could show that then he saw signatures of single rare earth ions or of single photons, which suggests single rare earth ions. Yeah. Another approach, and I like that one particularly, was done by Jeff Thompson in Princeton, where he used one of these nano-photonic cavities that I've introduced in the previous slide. So what you see here is this arrangement of holes. It's a cartoon here, it's not the real thing. Arrangement of holes. And this cavity was made out of silicon, so no rare earth ion here, but they put that cavity on top of a rare earth ion doped crystal, which is this green thing just below. Yeah, and if you do it correctly, well, the electric field is not completely confined to this nano beam here, but there is some evanescent field. And this evanescent field can couple to the rare earth ions that are sitting close to the surface of this crystal here. Yeah, and then as he changes the frequency of a laser across the absorption line of these rare earth ions, and then looks at how many photons are being generated from this device, well, he sees that at some point, well, he has lots of light, lots of lines that are very close together, a whole forest with no particular structure. But if he goes to the edge of the homogeneous absorption line, or inhomogeneous absorption line, he sees these individual lines. And this sounds a little bit like, well, it's a single thing where you emit photons, and around it, you don't emit anything. It sounds pretty much like this could be a single ion. And he could actually make measurements to show, indeed, it is a single ion, and come back to this a little bit later. Yeah, so we have two different approaches to observing single ions, observing photons from individual ions. So we thought, well, this is great. This is exactly what we need, a way to get around these long excited state lifetimes, which prevent us from making good single photon sources that we would like or that we need for quantum memory. So we just have to add these cavities. Yeah. And that's what we're doing. Yeah, and I'll show you here a little bit how you can actually do this. The whole thing starts with an idea of how your design should actually look like. I have to zoom in here. So what we wanted to do, what we did, is a structure made out of silicon, where you have a waveguide that becomes very narrow, and into which we can inject light, and the light travels down this waveguide. And here is reflected on the series of holes that constitute essentially a mirror as introduced before. At the same time, you have a waveguide here and one here, and this is also that also contain lots of holes whose distance and diameter changes at the center. So here and here you have these nano-photonic cavities. The light that's traveling down here actually couples to these waveguides and to these cavities, and then you have an optical mode here. Yeah, so that's the idea. How do we do this? We start with an idea of a device and a lot of simulations that tell us, okay, how wide is this nanobeam, how thick should it be, what is the diameter of these holes, how large is the distance between the holes, how should we do, what should we do at the central part here, where we have to change a little bit the configuration. At some point we have a device that we like, and then we take what is called a silicon on insulator wafer. This is something you can buy commercially, which is a very thin silicon layer of 250 nanometers thickness, sitting on top of a also quite thin silicon oxide layer. This is not to scale here. In our case, I think it's 3 micrometers or so, and the whole thing is sitting on 0.5 millimeter thick silicon, just as a substrate to hold everything together. Yeah. And then you can transfer this device here through some type of lithography, in this case, electron beam lithography, onto your chip. So the first thing is you cover the whole thing with persist, and then you eliminate all the parts where you would like the silicon to be removed using an electron beam, which you then just scan over your device and you make holes, or you show where the holes should be, where everything should be removed. And once you have done that, then you can do so-called reactive ion etching, or cryo-etching. You bombard the whole thing with ions. And the ions are such that they remove the silicon everywhere where your electron beam has written before. You see this here, you have almost vertical trenches. And wherever the electron beam has not written anything, the silicon stays. Yeah, the interesting thing is, while you remove the silicon down to this layer here, you may see this part here, this indicates where the silicon oxide layer starts. Yeah, so you can really make almost vertical trenches of, the minimum dimensions here are maybe 30, 40 nanometers or so. Yeah, so something very, very precise. And the next step, you dip the whole thing into hydrofluoric acid, and that has a particular property that it detects the silicon oxide. You should never store hydrofluoric acid in a glass container, it just eats through it. You don't want that. And you see what happens here. Yeah? So here is this trench. The silicon, the HF goes through this little trench here, and then eats away the silicon oxide and stops where the silicon substrate here starts, because it doesn't detect the silicon. Yeah? So by doing that, you can actually remove all material under this structure here, so that at the end, it is only connected through this pinch point here, through this tether, to the mainframe, and the whole thing here is actually just floating over the silicon that you have here. Yeah. Then you make electron microscope pictures, which is what you see here. Here you see another, this is an optical microscope. Here you see actually 1, 2, 3, 4, 5, 6, 7, 8 of these devices all together, tethered at one single pinch point to the mainframe. Yeah. And if this looks good to you, like this, well then you say, okay, I can come with an optical fiber. Let's say this is an optical fiber that I've thinned down to make it very precise. I can get close to this, and then I have from the Raths forces that makes this device stick to the optical fiber. You wiggle around, you can break it off here, and then you can move it carefully over and you place it on top of a rare iron doped crystal. The orange part here is an erbium doped lithium crystal. The brown part here is just nothing. So you see that these different waveguides, they stick out, and that is how we can then couple light into this. And then, you align the device with respect to this edge, put it close to the crystal, and now there are the Raths forces between your device and the crystal, and since the surfaces are much, much larger than the surface of my fiber, this force wins, and then clack, it attaches to the surface, and you can remove your fiber. Yeah, and then you can make measurements. In this case, you just look at the resonance, you scan, you change the frequency of a laser, and you see here there's a particular wavelength frequency where the transmission drops, or the reflection drops, you get transmission, so this is a resonance, and the width here tells you something about the Q factor that you require for resonance. Okay, so we have done that. We have the silicon cavity then sitting on top of a weakly doped erbium lithium crystal. This is interesting because erbium has a transition at telecom wavelength. This is the wavelength where optical fibers are very, very transparent. Yeah, so this is what we would like to use for quantum communications as well. So we have a memory that would work at this wavelength. We cool the whole thing down well below 1 Kelvin. The funny reason for that is that the dilution fridge was the only refrigerator that was available in the lab where we did it. And you don't have to go that far. And then, well, we did exactly what the other people have done before us. We changed the laser frequency. We send short pulses of light in, and then wait and observe photons. And at some frequency range here, we see that at some frequencies, we get a lot of photons out per second, and at other frequencies, we get basically nothing else. Yeah, so this sounds like a little bit like this could be peaks, photoluminescence peaks, due to the interaction with individual rare earth ions. And then if we look at the decay of the fluorescent signal, well, the red one here is what we measure with a standard crystal, no cavity. So here we see that it takes 1.8 milliseconds to change the fluorescence rate by a factor of 1/e. If we use no cavities, well, here's a decay that we have measured where we have an improvement of a factor of 15 or so, so this is much steeper. And the record that we have observed is this curve here, where we have an improvement of a factor of 140. Yeah, so that's quite a lot. And that really suggests that we're indeed working with a single ion. Well, it only suggests, it doesn't prove it. So if you want to prove it, there's one more measurement that we have to do, and this is called the autocorrelation coefficient. Look at the setup here. You have light coming in through this optical path. This can be an optical fiber or just a free space path. Here is a 50-50 beam splitter. So half of the light will be transmitted, half of the light will be reflected. And then here, and here you have a single photon detector. If you send a single photon in here, it is impossible for these two detectors to click to indicate the detection of a photon at the same time. A single photon cannot split. Either this detector clicks or this detector clicks, but never the two. Now you have to compare this rate with the product of this detector clicking or this detector clicking, or you can also compare it with the probability this detector clicks at some particular time and this detector clicks later. Because that must happen. If you create a photon here, one detector clicks. If you create a photon once again, it may be the other detector that clicks. Yeah, so you have to compare the probability of having two clicks either simultaneously, this one here, or at some time differences that correspond to the inverse rate with which you excite your device. Yeah, and you clearly see that the probability of detecting two photons at the same time is heavily suppressed when they should arrive or be generated at the same time compared to the other times. Yeah, and from the level of suppression here, you can actually gauge if you have single photons, which in this case means if you have single photon emitters. And here clearly we do. Yeah, so this is a very important step, not only about the creation of single photons, which is what we have generated, what we have demonstrated here, but we would have to do more, and we also want to make sure that these single photons, their frequency is not changing as a function of time. Yeah, we call that spectral diffusion. As time goes on, all the frequency wobbles around because in a crystal nothing is stable. You have spin flips in the lattice ions and so on. You have to make sure that that doesn't affect your spectrum. Otherwise, if it's changing all the time, you cannot think about doing multi-photon interference on a quantum network where you interface several photons, for instance, to make a projection on this belt, on the belt states, which is what you require for quantum teleportation. Yeah, so there are more things that we have to do, but this is already a very important thing. Yeah, so this allows us, opens the path to single and then also entangled photon sources. And another very interesting idea is to use this for quantum computing. So far we have thought about this as single photon sources. But if I'm able to see a single photon from a single ion, well, I can say, okay, it's my ion that does something, but actually the photon does something as well. And the photon, if you do it correctly, may tell you something about the internal state of your ion. And that is a way to read out your qubit state, because it's nice to be able to encode a qubit. At some point you also have to be able to figure out, okay, what is the state? And this can be done through the emission of a photon. For this you have to be able to observe the emission of a photon, which before was not possible. All right, how am I doing with time?
Yes, we have more 15 minutes.
50, okay, good. So I will just go on a bit and then we'll see how far I get. And so this was right now the interaction of light with individual red lines. And now I go to the other spectrum and I will tell you something about the interaction of light with large ensembles of rare lines. And I will actually start telling you why this is important for a quantum repeater. Now, I thought I'd put a nice picture here of a quantum repeater, and I Googled something up, and that's what I found. I'm not sure that's the way it looks in the lab, but I think it's supposed to tell you something about entanglement between these two places there. Yeah, so a quantum repeater is something about allowing you to create entangled photons or entangled ions or entangled atoms, whatever it is, some entangled quantum objects at a distance. Yeah, and the simplest way of doing that would be to say, okay, let's just create a pair of entangled photons and let's send one photon over there, and if it arrives there, well, I have entanglement between there and here. Yeah. The problem is the distribution or the transmission of a photon, the arrival probability, scales exponentially with distance, which I try to indicate here with this fading line. Yeah. Now you could say, okay, well, if it doesn't work, or it's not very likely, I can just try many times in parallel, multiplexing. Yeah, you can think of this like, okay, I use different optical paths, maybe different optical fibers, all in parallel. But you can also think of this, these are maybe different times, I try once after the other. You can think about this being maybe two different polarization components or orbital angular momentum states, whatever you want, you can add some degree of multiplexing. And of course, it does increase the probability for a photon to arrive here, but just by a multiplicative factor corresponding to the multiplexing degree here. It doesn't change the scaling. It was exponential to start with. It remains exponential. It may be so bad, it rapidly is so bad, that just multiplying with 10 or 100 or 1,000 won't make a gain in the thing. Yeah. But now, there's a good idea. What you could do is say, okay, I just split this long distance from here to here into several so-called elementary links. Elementary links, because this is kind of the basic unit, which repeats. Yeah, so moving from here to here, moving from here to here, moving from here to here. These 2 points are supposed to be in the same place. These two also in the same place. And now, let's distribute entangled photons across this link, and this link, and this link. Well, it turns out it's still probabilistic. It doesn't help us much. But what we could do is say, okay, let's multiplex across each elementary link. Let's try many times in parallel, many different optical fibers, rapidly one after the other, or maybe different frequency bins, whatever you want. And let's do it in a way that even though it's probabilistic, I can learn after the generation of this entanglement over which link it has actually worked. And that's the green line here. Yeah? So let's say after I've tried all that, I learned here it has worked, here it has worked, and here it has worked. Now what you can do now is release these 2 photons. They have to be stored in a quantum memory because you need time to learn that it has worked across the entire link. You can release these 2 photons, and now you make a projection measurement onto the set of Bell states between these 2. So let us suppose right now this qubit, this photon would be in a pure qubit state, as the one created by Edison? No, Aphrodite, exactly. Yeah. So what would happen then is, well, if these 2 are entangled, and you make a projection of the set of Bell states here, this one will show up in the origin state of this photon, teleportation. Well, now, turns out this doesn't have a state on its own. It is characterized by the fact that it's entangled with this one. Yeah. So the teleportation that we want to do here, or create or initiate by a Bell set measurement here, in this case, will not lead to transfer of a state from here to here, or a pure state from here to here, but will result in the transfer of entanglement between these 2 to entanglement between these 2. And if I do it here as well, and at the end I have generated entanglement between nodes that are very far apart. And it turns out this is much more efficient than this, and the reason for that is that here I have per default said, okay, this photon has to travel from here over this link to the very end. In this case, I haven't done that. I've broken down things into short links, and then I connect the short links that I knew that I know that worked. And that gives me a completely different scaling compared to here. And if you use that, in principle, in theory, you can go to arbitrary long distances. Yeah, so that's the idea behind the quantum repeater. And what we need for that, well, is the possibility to distribute entanglement over these short distances, is the possibility to put photons into quantum memory here. And I come back to this on the next slide, I believe, to make it clearer why you need that. But in short, you have to wait for information from somewhere else in the network that certain things have worked before you can use the photon in these memories. And you need a mechanism that tells you that you have been able to generate entanglement over these links. So let's go a bit more into detail. Yeah, I have it here. So this is zoom in of just one of these elementary links. How do we think about that? Well, on each end of such a link, we have a source that creates pairs of entangled photons. One photon we put into a quantum memory, so it's absorbed by some material in a way that we can read it later on. The other photon travels towards the center of this link. Same thing on the other side. I have entangled photons. One photon is put into a quantum memory. The second photon is sent towards the center. Here we make again such a measurement, a projection measurement of the set of Bell states. which, as I told you before, leads to the fact that right now the two other photons here will get entangled, in which case it means, well, I entangle my two quantum memories. Yeah, and they can hold these photons, so right now I have a resource. And you also see where this heralding comes from. But this whole thing happens only probabilistically, but if this measurement works, that tells me that one photon has to arrive from the left and one from the right. If one arrived from the left, well, that means a photon pair was generated here, and I have one photon left here. And if one photon comes from the right, that means I've created a pair here, and there's also a photon. So whenever this measurement works, well, then I know for sure that across this elementary link, I have succeeded. Yeah. So this is the way how you create these things. I can think about a lot of different properties, and of course, storage efficiency is certainly important. Or in general, you have to be able to store something at all. And there's one more thing that is particularly important right now in view of rare ions. What you would not like to have is a source that creates a pair here and a pair here. One photon is stored, and the other photon travels towards the center, and information about this has worked, or mostly this has not worked, going back. If you think about 100 kilometers between these two, this takes 500 microseconds. Yeah, and during 500 microseconds, your quantum memory is blocked because it can only be entangled with one photon. And then you may learn it has not worked, and then you repeat. So there is huge dead time in such a quantum repeater. Yeah, you don't want that. What you would like is a memory that can continuously receive photons. You send in the first photon that is a member of the first pair, and while the photon that is the second member of the same pair travels towards the center, you already create the second pair and send in another photon and another photon and another photon. So you just fill up these memories, and at the end you may fill this up with 10 to the 6 photons or so. Yeah. Which means here you cannot use a single ion, because a single ion can only be entangled with one photon. Here you have to use a large ensemble of ions. Yeah. And that brings you right now to these rare earth ions, these rare earth ion crystals, where you can create these large ensembles very easily with good properties to allow you using these memories. Yeah, so this is how to store photonic quantum states in a multiplexed manner, one after the other, or different frequency bins, or whatever it is, or a combination of those. Use large ensembles of atoms. Yeah, many of those. And there's lots of examples. You can use room temperature vapor, people do that. You can use laser-cooled atoms, and you use rare isotope atoms. How does it work? Well, there is one protocol, one way of doing it that is used right now in 6 or 7 labs around the world, I think, in which you start with such an inhomogeneously broad absorption profile. Lots of ions, each of one having a very narrow resonance line, but all these different resonances at slightly different frequencies, which is what this cartoon is supposed to show you. Now, let's suppose these ions have a ground state, an excited state. This is at the optical frequency at which you would like to store a photon. And then there are some other states here. In particular, there's one state that is very long-lived. Now, let's say I use a laser, let's say here, this green frequency, that I shine into my ions, into my crystal. This laser will be absorbed, or can be absorbed, but only by ions whose resonance is here. It can't be absorbed by the gluons here. So these ions will be pumped from the ground state to the excited state, in which case they can either fall back, in which case they would be pumped back up, or they fall down here, in which case they will just stay. If this level is long-lived, well, at some point you've moved all population from here, through here, into here. There are no ions here anymore, which means that your laser cannot be absorbed anymore. There are no ions here anymore, which means you don't have emission or amplification of your laser as you would have in an amplifier. You just have created a transparency window. Yeah, we call that a spectral hole. So you have, for instance, created a spectral hole here. There is no absorption anymore at this frequency. And now you can change the laser frequency a little bit and move it, let's say, to here, or here, or here. And by doing that, you can create a sequence of equally spaced, very sharp absorption peaks. We call that an atomic frequency clamp. Now, once you have this, you can send a photon into your device, and if the average optical depth is sufficiently large, the photon will be absorbed. Now, what is the state you create there? Which ion did absorb a photon? Well, they all participated collectively. You cannot pinpoint to a single ion. It's really a superposition of all these ions that contribute to the absorption. We call that a Dicker state. You can write it in this way here. We see it's the sum over all possibilities that one ion is excited. It's the ion J that is excited here, and all other ions are in the ground state, and then the sum goes from J equals 1 to n being the number of atoms. There's a normalization factor, doesn't matter. And then here are factors that depend on the position of the ion and that depend on time. So this is e to the I omega t part that we know from any wave description. Here I just replace the omega by 2 pi delta, because the delta is the detuning, it's the frequency difference of this particular ion with respect to the carrier frequency of light. You can transform things into this picture. Yeah. Now, if I look at that, I see that in the beginning for t equals 0, all these different cats come with the same phase, this part. As time goes on, all these different ions, all the different parts here pick up phase at a different rate because this delta depends on my ion J, and I get what I call dephasing. But if you look carefully, you take into account that the ions don't have random frequencies, continuously distributed frequencies, but a couple of discrete frequencies with equal spacing, well, you can just set t to be 1 over the frequency spacing you count here. This falls from the sky right now, but you will realize in a second why this is useful. And then this becomes 2 pi delta j. Oh, no, at this time here, then this factor 2 pi delta jt becomes 2 pi. This delta can only be an integer multiple of this conv spacing, because this is where my delta peaks sit. And then t, if I just plug this in, I see that at the end what I have is that these phase factors for this particular time are all an integer multiple of 2 pi. Yeah, and of course, the phase is only defined within 2 pi. So that means that all the different parts here have the same phase. You can think about constructive interference of all that. Sorry. So in a way, you have recreated the same conditions as those at the moment where you absorb the photon, but here it corresponds to the fact that at this moment, the photon will be re-emitted. And now you have a quantum memory with a preset storage time, which is determined by how you create your atomic frequency code, which is determined by the spacing here. Yeah, but it allows you in principle to store photons for a much longer time than you can do in an optical fiber. And this being preset is fine for quantum repeaters if you do it correctly. Yeah. What do you need for that? Well, you need an inhomogeneously broad transition so that you can actually create this atomic frequency count. If you have only one frequency, you can either remove everything or not. You need a long-lived auxiliary state for the optical pumping, and you need narrow homogeneous line width, because the narrower these things can become, this is limited by the homogeneous line width, the closer you can space them, and the closer you can space them, since the storage time is 1 over the spacing, the longer the storage time. So, and narrow homogeneous line width translates into a long coherence time. So you see all these properties all come together, and it turns out that reverse ions actually check all these different criteria. Okay, I will just quickly go through one experiment that we have done already more than 10 years ago. Not because it's the greatest and latest, but because it's one that is quite easy to understand, I think. So what we used here is a thulium-doped lithium niobate crystal. So thulium is one of these rare earth ions, and the transition is that of interest is at 795 nanometer wavelength. I will skip a lot of details here. What it is this lithium niobate crystal here, and then collaborators have actually indiffused thulium in this crystal. So you cover the whole thing with thulium, you stick it in the oven at 1100 degrees, and you bake it for a day or so, and the thulium will indiffuse into your crystal, and you see that thulium is actually occupying the first, 5 or 6 micrometers as measured from the top down. And after that, the collaborators also deposited a thin strip of titanium on top. I put it again in the oven. Titanium also indiffuses, and if you indiffuse titanium into lithium niobate, it raises the index of refraction. So this creates a waveguide, like an optical fiber is a waveguide with an index of refraction, the core being larger than the index of refraction around it. Same thing here. Yeah. And now it turns out that the guiding region of this waveguide, which you see here, extends down to 6 micrometers or so, which is exactly the depth over which thulium was in there. So we have a device that's already integrated, where there is already a waveguide, this thulium, and then, well, we can just couple light into it by butt coupling an optical fiber against it, and the second optical fiber from the other side. The whole thing is located inside the cryostat, and we have to apply a magnetic field in order to improve the properties. Okay, here is an overly full picture. I could spend an hour or so to explain you something. We don't have time for that. Just briefly, here is the total setup of the experiment. There are three parts of it, if you wish. One part is the source of entangled photon pairs, because you would like to store a member of an entangled pair and show that after recall of this member, the entanglement has not changed. So how do we do this? We start with a laser that emits short pulses of light of 6 picoseconds or so at 1047 nanometer wavelength. Then here is a nonlinear crystal. You use a normal crystal, you shine light in at a particular wavelength, frequency, and light at the same wavelength or frequency will come out. If you have a nonlinear crystal, you get effects such as frequency doubling, for instance. I think I mentioned that before. So here we get light at twice the frequency or half the wavelength. This is 523 nanometers. Now each pulse of light we send through an interferometer with a large path length difference. So light, each pulse is split at this beam splitter here. One part goes through, one part is reflected. This part here, the path length is longer than this part. And then here we have a second beam splitter. Again, half of each light pulse goes here, the other half here, which is then sent into our experimental setup. Yeah, so each pulse becomes 2 pulses, and in between these 2 pulses, the phase is not changing because this interferometer is very, very stable, it doesn't vibrate. Now, each of these pulses, or this double pulse, goes into a second nonlinear crystal, and there we use something like the inverse process, where each photon is split into 2. Yeah. Here you can think as if each photon here, as if 2 photons from the red laser are merged together to create 1 photon at a higher energy. But the inverse process is also possible. You can use a photon, you split it into 2 at half the energy, and of course this process has to satisfy energy and momentum conservation. Yeah. And then what you get from that is that you create, with a laser pulse, say 1 pair of photons. But since each laser pulse here is in a superposition of 2 different times, you will now create a photon pair with both photons belonging to a pair either emitted a little bit earlier, this is this quantum state here, photon 1 in an early temporal mode, and photon 2 in an early temporal mode, or both being emitted a little bit later, both late. And this is one of these belt states that aren't introduced before, but didn't use E and L, but 0 and 1. It's just the identification of early and late with a number. Okay, now this is this part here. Now these 2 photons, one is at 1532 nanometers. This is a wavelength where optical fibers are transparent. The other one is at 795 nanometers, which is where our thulium doped crystal absorbs. These 2 photons can be analyzed here and here. So you have to make projection measurements on 0 or 1. It's unintroduced, which means in this case, you have to ask, okay, is the photon coming early or late? The way you do this is you just use a detector with sufficiently high temporal resolution. And when it clicks, that tells you, okay, now the photon is at this particular time or at another time. But you also have to make measurements where you have projections into superpositions of early and late. And without going into details, in this case, this corresponds to adding an interferometer that looks very close to this one here. You see 2 different detectors because each projection measurement projects onto 2 orthogonal states, early or late, or early plus late, early minus late, 0, 1, 0 plus 1, 0 minus 1. So regardless of the basis into which you make a projection, you have 2 different detectors that have to indicate which of these 2 different basis vectors you projected. These are these 2 detectors here. So you have an analyzer here, you have an analyzer here, and then in addition we can add our quantum memory, and then, which in this case is the thulium niobate crystal inside a cryostat, go down to 3 Kelvin and exposed to some magnetic field, and then you can look at detections, you correlate detections, and from that you can reconstruct what you call the density matrix. It's a bit more general than the quantum state. It's the most, the best information you can actually extract for characterizing the quantum state. And this is what is plotted here. Yeah, so this is a 4x4 matrix, elements whose size, whose magnitude vary between -1 and 1. And here you see the density matrix visualized in terms of bars for quantum state without it being stored, and here after it being stored. And what you see is pretty much the same. Yeah, and you can make this more accurate. You can calculate quantities such as what we call the entanglement of formation. Not very important what it is. The only important thing is it is 0 if you have a quantum state or two-particle state that is not entangled, and it's 1 if it's maximally entangled. We see here it's not 0, it's not 1, it's clearly entangled. That's the good part. The other surprising thing is, well, with and without storage, there is no way of distinguishing between the two. So, of course, uncertainty in the measurements with memory was quite low. If you have sufficiently large, this is for the people who would like to do experiments here. Yeah, if you have sufficiently large uncertainty in your measurement results, you have a lot of way of interpreting it. Yeah, but within that uncertainty, you see that these two numbers have not changed. You have any other of these numbers that we can look at. Why are these numbers not perfect? Well, it has something to do with this particular solver entangled photons, which is not perfect to start with. That's why we're moving more towards single lines. And in short, well, we have been able here to store numbers of entangled states in a quantum memory for a very short time here, but that was the start. Release these photons and show that the entanglement was smoother. Okay, good. This is all this just a little bit longer. All right, so let me conclude that. What I've tried to tell you a little bit here is something about quantum networks. Why are they useful? Why are we looking at those? And well, that is quite a challenging problem. It includes lots of elements really from fundamental physics. In a way, you can even think of last century or 2 centuries ago physics, which is about spectroscopy. Quite often, we have some rare earth ion crystal. Nobody has looked at low temperature, and that's what you do. So it sounds like 1890 or so. But here, it's not just searching for things. There are reasons why we look at particular crystals with particular earth ions. Yeah, so very fundamental, and it becomes very applied at the end because our goal is to create quantum network technology. So it's really at the nexus between fundamental and applied science. You need a lot of physics, you need a lot of material science, there's a lot of engineering. It's a very rich field with a lot of different tasks. And if this is something that interests you, what you will learn about all these different things. Yeah, I also told you that rare earth ion doped crystals supplemented with photonic cavities, in particular nano-photonic cavities, but also larger cavities in order to improve the storage efficiency for these ensembles. Well, they're very well suited to create integrated and compatible technology that meet the requirements for building quantum computing nodes, for building emitters of single photons, and if you have those, you can also create entangled photons, and for building quantum memories for light based on ensembles. Yeah, so I find this exciting. I really love playing around with these fundamental things. I love playing around with the nanofabrication. I love thinking about extended photonic integrated chips where you have maybe some silicon chip that you put on top of a rare earth ion doped crystal, and then at different regions where you may create single photons, or where you store single photons. Maybe you have beam splitters and delay lanes and all that. Yeah, I think you can do this using modern silicon fabrication technologies. And then the rare earth ion gives you the active material that allows you to do everything that these passive things can't do. Yeah, lots of exciting things ahead. My group is quite new, as Anne said before. Well, we started in January this year. I'm actually a professor since 2006. Well, I did my PhD here in 2000. Then was a postdoc for a couple of years, and was for 12 years a professor at the University of Calgary in Canada, and for 3 years, I think, in Delft at QTech, and now since January I'm here. If this is interesting for you, you're looking for a master project or wherever you are, don't hesitate to contact me. We're looking for people who think there's a lot of interesting stuff to do. With this, well, thanks again for the organizers here. Thank you for your attention.
time for a couple of questions, and later discussion we can continue during the apero. So, do you have any questions?
Yeah, I want to ask a question. So, you did a very good job at selling these rare earth elements to us. And from what I understood, the reason why they're so special is because of some special transitions that can take place towards the outer shells. But then I saw in many cases you put these, so if you have the isolate ion, I get how it can work, but in many cases you put them in solids. So you don't, I think in most cases it was some perovskite structure. But then usually these outermost shell electrons are the ones that participate in bonding in this crystal. So how does it work if you put it?
So it's the 6s electrons that take part of bonding. These are all triply charged rare ions. You lose the 2 6s electrons and one of the 5p. And then there is still lots of 5 electrons around. Yeah, so the 4f electrons are still very much sheltered.
Okay.
If you look at the distribution function, you really see that they're much closer to the nucleus, and most of the 5 shell is still pretty much full.
Yeah, makes sense.
No questions? I have one.
Overwhelming, yes.
So when you were talking about entanglement to separate qubits via teleportation, does it have any connection with the quantum Zenon products? So that you just quantum Zenon products and have to measure the state actually this teleportation is somehow measurable.
So not with the quantum Zenon effect. There's none for me. The quantum Zenon effect is about if you have a photon in a particular state, let's say a horizontally polarized state, and if you project it onto vertical, well, then you won't get anything. If you make continuously projection measurements where you slightly change the angle of your projection measurement, remember what I told you after projection measurement, the quantum state is in the state corresponding to the outcome of your measurement. Yeah, so if you make a very small adiabatic change of the angle of your projection, in the end, your photon is in that state. So it's in the state that was orthogonal to the one it was in to start with. While normally, there is just no component of the state that's oriented horizontally to the vertical direction. Yeah, so it's a very interesting quantum effect, but it has nothing to do with teleportation.
Okay. Yeah, I have more questions, but we can continue during the apero. Thank you for coming, and next time we are going to have